Today we're going to talk about domain and range. So very, very nuts and bolts. Domain of a function. The domain of a function is all the possible x values. The range of a function is all the possible y values. So when I think about domain, what I really think about is what is x not allowed to do. And range is a little more complicated than that because it's usually, I have to look at the graph to be honest, like what can the range be? So let's talk about domain first. All possible values of x that can be plugged into the function and get a real number out. So here are the kinds of things that we can't do. And I guess I could read these words. We can find the domain of the function by looking at a graph. Sure, graphs totally help us see the domain. Or algebraic. Domain, there's three kind of main rules that we have to kind of look for. The domain of most functions we see are going to be all real numbers. Like every polynomial that we've looked at, like x squared or x cubed plus 5x, or anything that's just nice positive integer powers of x has a domain that's everything. So for example, f of x equal to 2x cubed plus 7x. There's no issues there. There's nothing x can't be because there's no rules we'd be breaking by letting x equals 1 or 0 or 5. This has domain all real numbers, which you can write in like 3 different ways. You can either literally write the words all real numbers, which I'm not going to do. You could write this fancy R symbol, which is just an R with 2 vertical lines instead of 1. Or you could write the interval notation, everything from the negative infinity to infinity, exclusive of the infinities because they're not real numbers. We can't ever really include them. Okay, so lots of functions have domain everything. But sometimes, a question. With the fancy R?
Yeah,
it's just an R with another vertical line. And what that R means all real numbers. What's a real number? 2, 3, 5/3, 0, -7. Any rational number is real. Any irrational number is real. Square root of 7, square root of 2, negative square root of 3, pi, e. Any number that, I know it's going to sound self-referential, but any number that is real. A better question is, what's not a real number? Well, imaginary numbers, like square roots and negatives, are not real numbers. We're not going to deal with them right now or really ever in this class, but that's kind of the other thing that we don't talk about. Oh yeah, imaginary numbers, definitely not real. If you're taking the 17 series, they are going to come up in 17C for sure, imaginary numbers. So they are in the future if you're taking the 17 series. In general, domains of functions are all real numbers unless there is one of the 3 following things. One thing is possible division by 0. Division has an S in it. So if you have something that has a fraction where there's a denominator that could equal 0, the way you're going to find the domain is you're going to find all the places that would make the denominator 0 and then exclude them. So we're going to set the denominator equal to 0, and then we're going to exclude all solutions. An example of this would be something like f of x equal to x plus 1 over x minus 2. What single value of x is not in the domain of this function? 2, right? X can't be 2, because if x is 2, you're going to get division by 0, which is undefined. So here, the domain, I'm just going to write for now that we would exclude x equal to 2. Great. That's one possible, what I usually call them the domain issues or domain problems, things that affect the domain or restrict the domain. The next thing is possible, I should say, instead of just square root, I should say possible even root of a negative number. So we can't take the square root or fourth root or sixth root or 1,000th root or any even root of a negative number. That's what results in imaginary numbers. So if you have a square root or fourth root or sixth root, we have to make sure that the insides of it are non-negative. So the way we deal with this is we're going to set whatever is in the even root to be greater than or equal to 0. I will just point out it's perfectly acceptable to take the square root of 0. The square root of 0 is 0. The fourth root of 0 is 0, et cetera, et cetera. So it's perfectly fine to have 0. It's perfectly not fine to have a negative number. Yep. I know. I feel like these boxes are like someone with finer writing than me made these boxes a little smaller than my hands are good at doing this. An example of this would be something like f of x equal to the square root of x minus 2. For this function, well, we need the insides to be greater than or equal to 0. So the way we would deal with this is we would say, oh, I'm going to set x minus 2 to be greater than or equal to 0, which would result in x being greater than or equal to 2. So here the domain would be all values of x that are greater than or equal to 2. 2, 2.1, 2.3, 3, pi, all the things, right? 1,000, a billion, but nothing smaller than 2, right? You can't have 1 or 0 or negative 3. Because if you plug in something smaller than 2, like 1 minus 2 is negative 1. And we can't take the square root of a negative. And that would be true if it was a square root or a fourth root or a sixth root or any even root. Okay, and there's one other, well, I should say, there's actually one other after this type of function that has a domain restriction, but we talk about that later. Those are called inverse trig functions, not for now. But the three main types of functions that have domain restrictions are possible division by 0, so something rational, possible square root of a negative, and then the last one is taking the logarithm of 0 or negative. So the possibility of a logarithm of 0 / a negative number. And we can't take the logs of 0. We can't take the logs of negative numbers. So when we have that, we're going to set whatever is in the logarithm to be strictly greater than 0. The way I often think about it is square roots and logarithms act very, very similarly when it comes to domain. The only difference is the square root, it's okay for the insides to be equal to 0. For a logarithm, it's not okay for the insides to be equal to 0. So an example that's very similar to the example I just wrote down for the square root would be something like f of x equal to the log base 3 of x minus 2. Doesn't matter what the base is. And our domain here, we would set x minus 2 to be strictly greater than 0. And our domain would be x strictly greater than 2. So here 2 would not be part of the domain. Here 2 would be part of the domain. Okay. Questions so far? When I ask myself, what's the domain of this function? The questions I really ask myself is there division? Is there an even root? Is there a logarithm? If none of those things are true, the domain is everything. So like in this prior example up here, in this function, I could say, oh, are there any fractions? No. Are there any square roots? No. Are there any logarithms? No. So I know the domain is everything. Like, Oh, and so when I say an even root, I mean like a square root or a fourth root or a sixth root, but not a cube root, not a fifth root. So that's actually a good question, a good point. If your function is something like, say, the seventh root of x minus 3, here the domain is everything. Because you can take the seventh root of positive numbers and of negative numbers. I know it's not nice, like if I said what's the seventh root of -2, I don't know, but I know it's real. I know there is a real number that if you multiply it by itself 1, 2, 3, 4, 5, 6, 7 times, you get -2. It's negative 1 point something. I don't actually know what it is, but this number, or sorry, this expression never has any values of x that can't be plugged in there. More generally, if I look at, say, something like the cube root of x, the domain is again all reals. We can take the cube root of any positive number and any negative number. What's the cube root of 8? 2. What's the cube root of -8? I know you guys know. What's that? The cube root of 1/8 is 1/2. The cube root of -8 is -2, because -2 times -2 times -2 is -8. So odd roots, domain is everything. On the other hand, even roots are problematic. If g of x is equal to the sixth root of x, I can't take the sixth root of -4 or -64, because you can't multiply something by itself 6 times and have it turn out negative. Right? If you multiply something by itself an even number of times, the result's going to be positive. Because a positive times 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 a positive is positive, and a negative times 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 negative is positive. It's too, right? It's an even number of negatives, right? It is too much, I agree. So this has domain x greater than or equal to 0. As far as the range goes, so the range of a function is all possible values of y that result from the domain. So basically any y you can get from the x values you're allowed to use. And for now, we're just going to do it graphically. So one example of this could be something like if we have the function 1/x plus 2. I know that's my typical 1/x function, which would usually have a vertical asymptote at 0 and a horizontal asymptote at 0, but it's going to be shifted how much, which way? Yeah, up 2. So my horizontal asymptote that was 0 is now going to be up 2 at y equals 2. So this is going to be graphically looking like this. My brain. Sure. So there's that function. And if I look at this, what's the only y value we're not getting? It's 2. Now I know sometimes a graph can cross its horizontal asymptote. So it's not like you have to be like given the graph kind of, we can't just like say graphing, like what's the range? But here, oh yeah, the range is everything except y equal to 2. So here's how we write the range using the interval notation. I want every real number except for 2. I want every real number from -infinity up to +2. And I use a parentheses to exclude the 2. Then a u union. And then I want everything from +2 excluded to infinity. That's every real number except for 2. On the number line, it looks kind of like this. There's 2. I don't want 2, but I literally want every number on either side of 2. So I want 3, I want 4, I want 2.1, I want 1.999, right? I want everything that's close to 2, just not 2 itself. And I want everything that's way away from 2 as well. I want everything, just not 2. So that's how we could write the range. I'll talk more about interval notation as we go on. Questions?
When do we know when we use the bracket?
So we use a bracket when we want to include a value. So and let's actually we'll look at some examples. Infinity never gets a bracket. You're right. Yeah, infinity is always parentheses because we can't include infinity because it's not a real number. It's just kind of an idea. Yeah, exactly. Okay.
How do you read that statement again?
Which statement here?
The negative infinity.
So I read this as the set containing all real numbers between negative infinity and positive 2, excluding 2, union everything from 2 to infinity, excluding 2. We'll practice a little bit more. If I can change my page. So we're going to, oops, let me just go down here. We're going to start talking about finding domain and range just by doing it graphically. So for this function, well, yeah, we know. So what kind of function is this? It's going to have the graph that's a parabola, right? It's x squared minus 2x minus 15. I don't particularly care how great it looks. What I do care about is what the range and the domain are. So the domain here, well, there's no restrictions, right? X, there's no roots. I should say there's no even roots. There's no logarithms and there's no fractions. So the domain here is going to be all real x values. Or if you prefer, everything from negative infinity to infinity. We're not missing anything. The range is a little bit harder because the range asks the question, what are the possible y values? Well, this parabola is going to have some lowest possible y value because it opens upwards. There's some bottom that we can't go below for the y values. Let's go ahead and find the vertex real quick. So the vertex, the x coordinate is going to be negative b over 2 times a, which is 2 over 2, which is 1. And the y coordinate is going to be, well, if I plug in the 1, I get 1 squared minus 2 times 1 minus 15, which is 1 minus 2 minus 15, which is going to be negative 16. So I also didn't give myself a very good setup here. I know my vertex is at 1, negative 16, which I'm going to draw down here, not very accurately. And then it's going to look something like this. This is not a good drawing of this parabola. All right. There's my lowest point at 1, negative 16. Talk about the domain. The range here, well, the y values go as low as negative 16. So we could write the range in kind of what's considered a less than, it's not the best way to do it, but it's not wrong to say the range is y is greater than or equal to negative 16. Those are all the possible y values. Y can be as low as negative 16, and then it gets higher and higher and higher up to infinity and beyond. Now, in interval notation, here's how we're going to write that. You're going to have a bracket with a negative 16 because we want to include that, and then we want everything that's larger than that. I often, if I'm doing the interval notation, I like to draw it on a real number line. So I'm thinking about my y values. I'm like, okay, y can be as small as negative 16, and I can include that. And then I want everything to the right. I want all of this. So, oh yeah, I want everything from negative 16 inclusive, and then over here is infinity. That's my range. So all my possible y values. I will admit, fully, range is kind of it always feels like a dicey proposition because first we just talk about it graphically, and then in the next class, we're going to talk about how you can find it using some analytical methods. Specifically using the inverse function is how we also talk about finding the range. Let's look at this next example. I want to find the domain and range of this logarithmic function that's been shifted around a bit. So I know, I think you guys know too, this function has been shifted left or right? Left. So it's left 1 and up 2. And so I'm going to think about where my original intercept would have been. The original logarithmic function before it was shifted would have had an intercept at 1, 0. And that's going to shift 1 left and up 2. This will be there. And I also know that my vertical asymptote, which would have been at the y-axis, the line x equals 0, is going to shift 1 left. Shifting a vertical asymptote up 2 doesn't change it. Right? If you take a vertical line and shift it up, it's still the same vertical line. So my vertical asymptote is over here at x equal to negative 1. I'm not going to draw vertical asymptotes. And it's going to have the usual logarithmic shape. I don't really care what my x-intercept is. I just care that my shape looks like that. All right, so domain. Well, right, domain is the possible x values. And just looking at the graph, we can see, well, x can't be negative 1. That's our vertical asymptote. And x isn't anything to the left of that either. So we can see for sure that x has to be bigger than negative 1. Or in the interval notation, right? Actually, let's draw the picture before I start talking about the interval notation. If negative 1 is the point of we don't want that and we don't want anything over here, we want all of this. So we want everything from negative 1 not included up to infinity. How about the range?
I was gonna say, so it's not a bracket because you don't want negative 1.
Right. We only use a bracket if we want to include that value. We use a parenthesis if you want every value up to that one, but not that one. So what that parenthesis is saying is you're getting all the numbers that are really, really close to negative 1 on the right side of negative 1. Right? You're getting negative 0.9 and negative 0.99 and negative 0.99999. Right? You're getting all these values that are really, really, really close to negative 1 on this side, but nothing over here, and not negative 1 either. But I want to make the point, because I've seen many students make this mistake in the past. People are like, oh, if I'm not starting at negative 1, then I'm starting at 0. That's not the case, right? We're getting all these numbers between 0 and negative 1, right? So, we want everything up to negative 1, just not that particular value. Range, on the other hand, here is not too terrible to see. So, right, it's all the possible y values. And let's see, the y values go down as far as you want to negative infinity. How high up do my y values go? It is infinity, right? It kind of looks like it could maybe flatten out at some point, but it doesn't ever. So a logarithmic function, if you graph it on Desmos and really zoom out, like it looks like it kind of just flattens out because like it grows so slowly. But any logarithmic function does have a range that's everything. It always gets larger and larger and larger. It just takes a really long time. So the range is everything. Great. So if you have questions on the Zoom, please ask them. You can always ask. Awesome. All right, let's look at a couple more graphical ones, and then we'll do I think what the more interesting part is the actual kind of analytical stuff. Well, let's go ahead and look at these next two graphing ones as well. Once again. So let's find the domain and range of e to the x, which again, we've already kind of talked about before, but it's good to see again. So let's graph it. E to the x has the usual exponential shape. What's our intercept?
0, 1.
Right. Someone's gonna say just 1, which is fine. It is 1, but it's actually say, what's the y-intercept? And you guys are right. It's 0, 1. And there is no x-intercept unless you shifted it down, which we haven't. So this is gonna have this sort of shape. And when I look at e to the x, I know I'm talking about doing it graphically, but I'm still thinking about domain in the, do I have any of those 3 problem types of functions? And I don't. There's no fraction here. There's no even root. There's no logarithm. So I know just by seeing those 3 things aren't there, the domain has to be everything. So domain is everything from negative infinity to infinity. The range, on the other hand, is limited. We don't get all the possible y values. What y values do we definitely not get? What can't be negative. Okay, let me ask you guys. Do we get a y value of 0? No. Do we get any y value that's bigger than 0? So I can get like 1 billionth, right? Which is definitely smaller than 1. Yeah. So my range here, which again, I'll just remind you, is the possible y values. Well, it's going to be y is greater than 0. It can be really, really small, but it can't be 0.
You put it as equal to or greater than 1.
No, so that's a really good question, and the answer is no. So this is not the same. So I should be a little more clear here. No, but there's something I want to say though. So in most contexts, these are not the same. Y greater than 0 and y greater than or equal are not the same thing. But there are some contexts where that is the same thing. Specifically, when you're taking like statistics and you're talking about things being discrete, meaning like you're talking about, say, the number of people that do a thing, then y bigger than 0 and y bigger than or equal to 1 are the same, because you can't have 2/3 of a person. So in some contexts, they actually do mean the same thing. Not graphically, but yes, in other things. So I don't want to leave you with the feeling that they can't ever be the same, because they actually kind of can. But yeah, here they're not the same, because there's lots of values between 0 and 1, like a half or 2/3 or 1 billionth. So our range here is everything that's bigger than, but not including 0, which we write that way. All right, this gives you all the numbers that are as close to 0 that you want, that are bigger than 0. Okay. You guys are asking good questions. I appreciate the good questions. I appreciate bad questions too. I don't say questions are bad ever, and sometimes I would never say it, but like sometimes questions like, oh well, it's still a good question. I can make something out of that. But please ask the questions. Even if you think it's a terrible question, ask anyway. It's going to be illuminating. So here we definitely have one of the known problem functions for domain, right? We have got a square root of x plus 9. We could just graph it. That square root of x plus 9 is going to be your usual square root function, shifted which way? 9 to the left. So I'm going to start off the chart, way over here at 9. I'm going to have the point -9, 0, because if you plug in -9, you get the square root of 0, which is 0. And then it's just going to go up and up and up. I know if I plug in 0, I'm going to get 3. And if I plug in -5, I'm going to get 2. And there's our graph. And visually, we can see all the things. We can see, extend this x-axis here. We can see that the possible x values, well, we don't get any x values less than -9. So x has to be greater than or equal to -9. Which in the interval notation, we would say, well, in fact, let me draw the picture, right? Here's -9. We want everything starting at -9 to the right. We want a bracket -9 to infinity. One thing to say about the interval notation is whenever you're writing it, the correct way of ordering things is always the smaller numbers on the left and the bigger numbers on the right. So it would be, yeah, it would be incorrect to write the domain here as this.
Facing the other way. Is flip the.
So, oh, yeah. In fact, we'll do that in a second. Yes, I see what you're asking. Yeah, just give me one moment. So, yeah, in fact, actually, so if our function was instead, say like, let's say it was going this way. So it's the square root of, it would be negative x 9 minus 9. If that was our function instead, which is reflected and shifted 9 to the left, or I suppose I said it shifted 9 to the right first and then reflected over. So it looks like that. Honestly, the way I came up with this is I thought about what the domain needed to be, and I know that if x is -9, it works, because negative 9 is 9, and 9 minus 9 is 0. And if x is more negative, like -10, negative 10 is 10, 10 minus 9 is 1. Oh, we're safe. I can take the square root of 1. Here, the domain would be everything from -infinity up to -9. Like that. So you always write the smaller number on the left, the larger number on the right. Or the more negative number on the left and the less negative number on the right. Or just look at the number line, right? If I was trying to write this, I'd be like, okay, well, what's more to the left? Negative infinity or negative? Negative infinity is always the most to the left. Right? You can't be more left than negative. You can't be more right than positive. So, yeah. The range here, we can see, right, for possible y values, the range is going to be, we get 0 this time? Can y equal 0? Yeah, it can, because that point there is filled in. That's definitely the point where x is -9 and y is equal to 0. So we do get to include 0 and then everything that's larger than 0. So we're going to go 0 to infinity. Okay. So graphically, domain and range, maybe not too terrible, maybe still kind of terrible, but definitely something that people like to talk about, like to ask about. I seem to have an extra page here. I don't, I do. So now we're going to talk about finding the domain and range without using the graphs, especially because some of these things are really hard to graph. I don't want to graph. You totally could, if you're doing homework, do this the way we're going to do it, but then also you could look at Desmos and be like, hey, what is x actually not allowed to be? Right, we're not asking about range here, so I have to look for the y values, just the x values. And actually, I'll say a little bit more about that after this first one. So this first one, I've got a fraction, and I know I can't do what? I can't divide by 0. I want to be extra clear here. Could x be 0? For sure, 0 is definitely in the domain. If x is 0, you get 0 plus 2 over 0 minus 49, which is definitely a real number. It's -2/49, whatever that is, but it's definitely real. So what we're going to do is we're going to set, I even like to write exclude. We're going to exclude where the denominator is equal to 0. We're very exclusive. I mean, when it comes to dividing by 0, right? So there are going to be two values we don't want. X can't be 7, x can't be -7. And you can either do this by actually just adding the 49 over there, or you could factor. Either way is perfectly legitimate. Just be careful, right? If you do it the other way, where you set x squared equal to 49, make sure you do get both the positive and the -7 as your exclusive solutions. So we're going to exclude x equal to 7 and x equal to -7. Those are the only things we don't want. We want everything else. I do find it helpful if I'm writing the interval notation to draw this picture. I'm going to draw the number line. And on the number line, I only want to put the values that are coming up. I don't care about 0. I don't care about 5. I don't care about 80. I only care about the numbers that I'm possibly excluding. I don't want -7. I don't want 7. I do want all of the rest. So notably, I'm going to have 3 separate intervals that are broken up at these 2 spots. Going from left to right, that's the way we should write it down. From left to right, I'm going to have everything from -infinity up to -7, but excluding -7. So I want everything from -infinity to -7 with a parentheses. Union, everything from -7 to 7. I want everything in between those two. So -7 to 7. So this interval here includes things like -6 and -4 and +5 and +2 and -6.99999 and +6.872, right? Anything between -7 and 7. And then finally, we want this third interval, everything that's bigger than 7 and beyond. And I will mention, one second, okay. I'll mention that if you're excluding a specific number of just points, right? Here we excluded 2 points. You're going to get 3 separate pieces union together. If we were excluding 5 points, there would be 6 pieces. There's always one more piece than what you're excluding, right? Because every time you exclude a point, you break it up into 2 new or an extra new piece. Erica.
Would it make sense if you put a bracket in front of the -infinity?
It would not. And the reason why is because -infinity is not a number. So I'm not ever saying, because I'm not saying x can be -infinity. What I'm saying with this notation here is that x can be any negative large number. So can x be -1 billion? Sure. Can x be -1 trillion? Sure. Can x be negative a Google? Yeah. X can be as negative as you want it to be, which is indicated by this idea, this notation, this thing that's not a real number. But yeah, we don't use a bracket there because it's not a real number. And just to be very extra clear, we never use brackets for infinity or negative infinity. Always parentheses, because they're never actually included, because they're not real numbers. Let's look at another example.
Oh, excuse me, James.
Oh yeah.
Sorry, I had a question about something.
Go ahead. Yeah.
Can you remind me the difference between like when the U in the middle is upwards and that or downwards?
We're never gonna have to deal with the downwards one here, but the difference is when the U in the middle is upwards like this, which is a union, you're saying X can be in here or in here or in here. When the symbol is turned over, which is called an intersection, it means X has to be in the first part and in the second part. So you're basically trying to find where they overlap when you're talking about an intersection, which is not anything we're going to talk about for this particular thing, but good question. Yeah, we don't, when you're writing domains or ranges, the union symbol is the only one we ever need to use. We don't use the intersection symbol. Hopefully that clarifies. Although there's a way you could use the intersection symbol, but I'm not really going to, because it's more work than it's worth, to be honest. It's easier just to kind of think about it than to see like it's this interval will overlap with this interval, and then well, I might have an example if we have time. So let's look at this next one. So I see a couple things. I see fractions. I see a square root. So we could do it in 2 pieces. We could say, well, I know the denominator can't equal 0. So I need to make sure that the square root of x plus 8 doesn't equal 0. I usually like to write the words exclude x plus 8, square root of x plus 8 equals 0. And what's going to be the only value of x that's going to be a problem there? What's going to make that equal to 0? -8. So I'm going to exclude x equal to -8. I don't want that. But then I also have a square root. And I know that the stuff inside the square root needs to be greater than or equal to 0. So I want the stuff inside the root to be greater than or equal to 0. Do be careful, right? I'm not setting the square root of x plus 8 to be greater than or equal to 0. I'm setting the stuff inside the root, or the argument of the radical, to be greater than or equal to 0. Right, but we're not saying this. And we don't want to do that. And so we're going to get x greater than or equal to -8. But combined, we want x to not be -8. We want x to be bigger than or equal to -8. So we really just want x to be bigger than -8, which we probably could have figured out by looking at it, right? We say, oh, we want the insides to be greater than or equal to 0, but they shouldn't actually equal 0 because we're taking the square root of 0. So we probably could have started with just saying, oh, we just want x plus 8 to be strictly greater than 0. Because we know we don't want it to equal 0 because we'll be dividing by 0 if it's equal to 0, which would lead us to x greater than -8.
So either one of those could, they're like possible ways.
Yeah, totally. And so what I would say, so after, like, I've obviously done this for a while. With practice, you start to see that, oh, if you have something in the denominator, even if you got some extra domain restrictions, you know you don't actually want it to equal 0. So whenever I see a square root in the denominator, I'm just like, oh, I normally would set the insides to be like greater than or equal to 0, but if it's just the square root of all this stuff, I'm just going to set it to be greater than 0. So here our domain would be everything from -8 with the parentheses because I don't want to include it, all the way to infinity. All the way to larger and larger and larger. We don't actually ever get to infinity. Okay. Let's look at these last couple ones. So for this one, again, I've got two things going on. I want to exclude where the denominator is equal to 0. So I'm excluding x squared plus 7x plus 10 equal to 0. That does factor. So I want to exclude x equal to -2 and x equal to -5. And if I'm going to do this, I really do like drawing it on the number line. I think it's nice. So I'm going to start off. I know I don't want -2. I don't want -5. So far, I want everything else, but I'm not done. And because in addition to not wanting to divide by 0, I also don't want to take the square root of a negative. So I also have to set the insides of the square root, or the argument of the square root, to be greater than or equal to 0. And here it's perfectly fine for it to equal 0 because it's in the numerator. It's perfectly okay to have 0 in the numerator. So I'm going to isolate x. I'm going to get x greater than or equal to, well, I should do 2x greater than or equal to -5, x greater than or equal to -5/2. And on the number line, it might be helpful to write this as a decimal. I want x to be greater than or equal to -2.5. So -2.5 does live between -2 and 5. It's a little bit less than -2. I don't need to be precise with like my distance is. Let's just say it's right there. So that's -2.5. Okay, if x is bigger than or equal to -2.5, do I want everything to the left or everything to the right of -2.5? To the right, right? Bigger than means to the right. I should say x bigger than something means x is to the right of that something. X smaller than something means x is to the left of that something. So I want everything including -2.5 and then everything bigger than it, except for -2. We already know that we don't want -2. I don't want any of this garbage to the left. I mean, okay, those are perfectly good numbers. I shouldn't call them garbage, but I don't want those. They're not what are in my domain. So here my domain is going to be everything starting at -2.5, inclusive. We definitely get to include -2.5. And then everything between -2.5 and -2. But I don't want -2 because -2 would make me divide by 0. And then everything from -2 onward. Nothing to the left of -2.5. Yeah.
How come you set the numerator equal to 0 for this one, but not on the top
So I'm not, so are you talking about this part here?
Yeah, like you took the root.
Right, I took the stuff inside the root
Yeah.
and said it had to be greater than or equal to 0. Which now I know I still solve that like it's equal to 0 because that's what we do. But this other one, I didn't worry about the numerator because the numerator didn't have any problems over here because there wasn't a root in the numerator. So it's all about the fact that it's a root, not that it's actually a numerator. Yeah. Yeah.
So how does like that correlate with excluding the denominator as well?
Should I say that one more time?
Like how does that, how can you, because I just stopped at the bottom and used that, so how can you have, you incorporate both the numerator and the denominator into finding the domain?
Well, that's what we've done. So I agree. I 100% like that you factor the denominator. That's a perfectly good way of doing it. And you saw when you factor the denominator that right, x couldn't be -2 and x couldn't be -5. So what we are kind of doing here to kind of go back to what I don't know who actually asked the question, we are kind of overlapping our domains. Right? We're kind of saying for this one, for this piece, x can't be these two things, and for this piece, x has to be greater than or equal to 0, which is all this. And then we're saying we want kind of the least amount of stuff that still satisfies both those things. So we want x to be greater than -2.5, greater than or equal to -2.5, and then we don't want -2. So I don't know if I really answered your question very well. How much time have I got? Not enough time ever. Let me go ahead and we'll come back to this one here. I want to show you guys one other example, which I think might help a little bit. So yeah, let's do this one. Let's find the domain of f of x equal to the square root of 4 minus x plus the square root, let's see, x minus 1. Okay. So we've got two competing, well, not competing, we've got two things we have to worry about. Right? In this first piece here, we're going to say, well, I need 4 minus x to be greater than or equal to 0. I would probably make the choice of adding x to both sides and saying 4 is greater than or equal to x, and then maybe rewriting it and just saying, oh, which means the same thing as x being less than or equal to 4. Or if you prefer, you can do the thing where you subtract -4 to the other, or subtract 4 to the other side and have negative x bigger than or equal to -4, and then multiply both sides by -1, which changes the direction of the inequality, and get x less than or equal to +4. Either way, you get the same thing. It just depends. So what? Because when you multiply both sides of an inequality by a negative, you change the direction. Here's my evidence of that. 2 is less than 3. We're all cool with that. If you multiply both sides by -1, is -2 less than -3? It's not, right? -3 is further left. It's the one that's less. So whenever you multiply both sides of an inequality by a -1 or negative anything, you have to change the direction of the inequality. That's what's happening here. We multiply both sides of -1. I didn't do that. So in the red one, what I did instead was I added x to both sides. And then I just said, well, x less than or equal to 4, I can rewrite that as x less than or equal to 4. Not absolutely necessary to write this, but I find it helpful to write my x on the left so I can kind of read it better. Okay. I know it's 10:50. If you need to go, please go. But I'm going to finish this problem because I want you all to see it. So go if you need to, but stick around if you can. I'm going to write this one as x minus 1 is greater than or equal to 0. And this one's much easier to solve. This is just going to be x greater than or equal to 1. Okay, so one way of handling this would be just to say we need both. We need both x to be bigger than or equal to 1 and x to be less than or equal to 4. So I want everything between them. Which makes sense because x can't be 5. If x were 5, we'd have problems here. X can't be -1 because if x was -1, we'd have problems here. But here's another way of looking at this that I think you all might want to see. And again, back to the person, hopefully they're still around, who asked about like the intersection. This is where you could actually think about the intersection. So if x is less than or equal to 4, well, that's everything left of 4, including 4. And if x is bigger than or equal to 1, that's everything bigger than or equal to 1. And what I want is I need both of them to be true. So I need the overlap, also known as the intersection. That is the intersection. So if you really wanted to make this complicated, which I don't, but if you wanted to, you could say this is the intersection of this red part, which is everything from -infinity to +4, intersected with the green part, which is everything from, I know my 1 kind of got lost there. Sorry, that's a 1. From 1 to infinity. And then their overlap, I can't look at that and know what the answer is. I have to actually look at the picture and be like, oh, well, they overlap from 1 to 4. So their overlap is bracket 1 to bracket 4.